Welcome class to this video on direct variation. In this video I'm going to introduce the concept of direct variation, go over its key characteristics, and then introduce you to the kinds of questions that you will see on assignments and eventually on your quiz. Alright class, I have a confession to make. Since quarantine began, I've been eating way too much candy. In fact, I timed myself the other day and I was eating 2 candies per second. Now, when I first grabbed the bag, I hadn't eaten any candies yet, obviously. And on the table of values you can see represented in the middle of the screen, you can see that I could represent the fact that I had grabbed the bag and not eaten any candies and not began timing myself by putting 0 for time and 0 for the numbers of candies eaten. Now what you're going to see is you're going to see each set of 2 candies as each second passes. And you're going to see the table of values be completed as we go along. So there you go, 1 second, 2 candies, 2 seconds, 4 candies, 3 seconds, 6 candies, 4 seconds, 8 candies, 5 seconds, 10 candies, and then 6 seconds, I had already consumed 12 candies. 12 candies too many for sure. Now we're going to repeat this process, and what I want you to notice when we do it this time is that on the graph, you're going to see the points plotted. The points that we're going to plot is going to be showing the relationship between the time passing and the numbers of candies eaten, and they will reflect the points that you can see labeled here or listed here in the table of values. So let's watch that. 0 seconds, there you go. Look at over here, you can see the points being plotted on the graph. At 0 seconds, 0 candies had been eaten, so the point is 0, 0. At 1 second, 2 candies had been eaten, so the point is 1, 2, and so on and so forth. Once you've normally finished plotting the points of a relation, you then draw a line through the points to represent the relationship between the 2 variables. Now I want to ask you a question that you should be familiar with. What is the rate of change of this graph? We learned how to do rate of change in the previous section in the course. When you're doing rate of change of a graph, all you have to do is find 2 points on the graph that you can clearly identify, and then draw a right-angled triangle between them. So for this one, I'm going to use the point 1, 2, and I'm going to use the point 6, 12. I could use any combination of 2 points I can clearly identify all along the line, and I would get the same answer. Now that I've identified my 2 points, I can draw my right triangle between them. Here you can see my rise and my run. Now the number 10, I got the number 10 because I went from 2 to 12. 12 subtract 2 is equal to 10. So the rise is the difference between the larger and the smaller number, and in this case it is 10. Then I went from, on the x-axis, from 1 to 6. From 1 to 6, and I do 6 subtract 1, and I get a run of 5. I can now use the formula that I learned in the previous section, rise over run, and I get 10 divided by 5, and I can see that the rate of change is 2 for 2 candies per second. Alright, one important thing to notice here is that when we were doing rate of change for time-distance graph, the rate of change represented speed. In this case though, because we're looking at time versus the number of candies eaten, the rate of change represents the number of candies eaten per second. Another word we use for rate of change I mentioned before is slope. And for some reason in math we use the letter m to represent slope. I know it doesn't make very much sense because the letter m is nowhere in the word slope, but this is a convention in math that we will be following. Now we're going to try to connect the scenario that I just described with the definition of direct variation. Direct variation is a relationship in which 2 quantities vary directly with each other. The dependent variable is a constant multiple of the independent variable. And direct variation is also sometimes called a proportional relationship. Or you could say that direct variation describes a proportional relationship. I know that's a lot of words right now and maybe a little bit confusing, but hopefully by the end of this screen, we'll have a good sense of what that definition's all about. When we write direct variation as an equation, we write it in the form y equals mx. I'm now going to show you the different components of y equals mx and try to relate it to the definition that we just read. Y is our dependent variable. If you look at the definition, it said a relationship in which two quantities vary directly. The dependent variable is one of the quantities, one of the things that you can count. So if you think of the scenario we did before, which of time and number of candies eaten would be the dependent variable, the variable whose quantity depends on the quantity of the other variable? Well, the dependent variable in this case would be the number of candies eaten, because how much candies Mr. O'Connor has eaten depends on the amount of time that has passed, and not the other way around. So that's the y part of y equals mx plus b. What about m? Well, we just learned or reflected on the idea that m refers to rate of change, which can also be called slope, and which can also be called, and we'll come to this a little bit later on in more detail, the constant of variation. That is m. Now the third component of y equals mx, which is x. X represents the independent variable, and that is the other of the two quantities that vary directly with each other. In our scenario, which was the independent variable, time or number of candies eaten? Time was. Time does not depend on the number of candies eaten, but the number of candies eaten does depend on time. That makes time the independent variable. And just a hint, time is always the independent variable because we cannot affect time. And we've discussed that several times in class already. So let's now try to write the equation for the scenario of Mr. O'Connor eats 2 candies per second. And then we'll start to be able to understand, hopefully, this second sentence here. All right. What was our dependent variable from our scenario? It was the number of candies eaten. Therefore, n equals, n is our dependent variable, n is representing y. N equals what? What was our rate of change? Our rate of change was 2. We had a slope of 2. What was our independent variable? It was time. So instead of writing x, we could write t. Now for n, I could have written, for example, c for candies. That would work too. It doesn't matter really which variable you use, but usually you want your variables to be related to the situation. T is for time. I could have maybe also used s, as in for seconds. As long as the variable is related and somewhat to the situation you're describing, it will work. Now I want us to reread part of the definition. The part of the definition that says the dependent variable is a constant multiple of the independent variable. When it says it's a constant multiple, that constant multiple is referring to the rate of change, the slope, or what's called the constant of variation. In our situation, it's 2. And so what this sentence means for our situation is that n will always be the result of multiplying t by 2. And so all of the values that will be along the line are going to be multiples of 2. All the y values are going to be multiples of 2. And they will vary directly. So let's see that in practice. If I substitute, for example, 0 for t, I get 2 times 0, which gives me 0. That means that on the graph, there is going to be the point 0, 0. The first 0 is for t, time in seconds, and the second 0 is for the number of candies eaten. And you can see that point on the graph there. Let's try that again. And I'm keeping down here at the bottom the how the coordinates work. So you can see each time we get an answer, we are getting an answer that is in the form x, y, or in our case, because x in this case independent is time, and n is number of candies, y, it's going to be tn. All right, so let's see how this works now. If I substitute in 1 for t, I get 2 for n, and therefore I get the point on the graph 1, 2. And you can see that 2 is a multiple of 2 because it is 2 times 1. You would find that point 1, 2 on the graph right there. Again, what if I substitute in 2 for t? 2 times 2, I get 4. Is 4 a multiple of 2? Of course it is. It's the result of 2 times 2. So 2, 4 is a point on the graph. There you can see it, 2, 4. So you can see the values we get for y are all going to be multiples of whatever this number is here, the constant of variation, the constant multiple. And so I'll let you see the last few a little bit faster. 2 times 3, we get 6, means there's the point 3, 6 right there. 2 times 4, we get 8, means we have a point on the graph for 8. You can see it there. 2, 5 equals 10, and so we have a point on the graph 5, 10, which you can see right there. And now I think you understand the basic idea here. If I substitute a value for t, whatever value I substitute for t, my answer for y will be that number for t times the constant of variation, or the rate of change, which is, in this case, 2. Let's take a look at another scenario. In this scenario, Ian earns $50 per drawing that he sells. Hope you're making a bit more than that, Ian, but let's just work with that number for now. So if Ian sells 0 drawings, we would all agree that Ian should earn $0. And so on our table of values, we would have the values 0, 0 as our first set of values. On our graph, we would also have the point 0, 0 plotted. So now what we're going to see is we're going to see as Ian sells each drawing and collects his $50, we're going to see the values be completed on the table of values all along here. And then we're going to see at the same time the points plotted on the graph. One drawing he gets 50, 2 drawings he has 100, 3 drawings he has 150, and you can see it on the graph as well. 4 he has $200, 5 he has $250, 6 he earns $300. Once you're finished plotting the points, we can draw a line to represent the relationship between the number of drawings that he sold and the money earned. Now, just like last time with the last scenario, let's think about what is the rate of change. Remember how we find rate of change? We draw a right angle triangle between any 2 points that we can clearly identify. I've chosen to do 0, 0 and 6, 300. And so I can draw my rise. I went from 0 to 300. That's a rise of 300. And I went from 0 to 6. That's a run of 6. I use my formula, which is rise over run, and I get 300 divided by 6. I then get $50 per drawing. So reflect, when we did time distance graphs, the rate of change, the slope, that meant speed. When we did the previous scenario, the rate of change represented the number of candies eaten per hour. In this situation, the rate of change, or the slope, represents $50 per drawing. And again, m is the variable we use for slope, so m is equal to 50. As we did with the other scenario, we're going to use this scenario to try and reflect on the definition of direct variation. As you recall, when we write direct variation as an equation, it is in the form y equals mx, where y is our dependent variable, m is our rate of change or slope or constant of variation, and x is our independent variable. So, looking at the definition again, where it says a relationship in which 2 quantities vary directly with each other, let's first identify the quantities that we're working with from this scenario. Here we have drawings sold and money earned. If we want to write an equation for the situation, which of these 2 quantities is the dependent variable? It is money earned. Money earned is the dependent variable because it depends on how many drawings are sold. What letter could I use for money earned? I could use M, I could use E, either will do. For now I'll use E. Now, what was our rate of change from this scenario? Our rate of change or slope was 50. And so instead of writing M, I can write 50. What was our independent variable? Our independent variable in this situation was the number of drawings sold. It's the independent variable because it is not affected by the money earned, but instead it has an effect on how much money is earned. If he sells more drawings, he'll earn more money. And for each drawing he sells, he earns in fact $50. So instead of writing X, I can write D to represent the number of drawings being sold. Looking back at the definition, it says the dependent variable is a constant multiple of the independent variable. Well, it's going to be a constant multiple in this case of 50, this constant of variation here. Each time I put in a value for D, I will get a multiple of 50. So let's see that with the first couple values. If I put in 0 for D, I get 50 times 0, I get 0, 0, which is the set of coordinates 0, 0. And D is the first 0 for drawing sold. E is the second 0 for money earned. And you can see that on the graph right there. What about if if Ian sells one drawing, then he earns $50. That is the point 150. And you can see that on the graph here. 50 is a multiple of 50 because 1 times 50 is equal to 50. And 50 times 2, 2 times 50 gives me 100. That means there's a point to 100. You can see that on the graph right here. And hopefully you're getting the point. Each time I substitute a value for D, the X variable, Y will be the result of multiplying that variable by the constant of variation. So all the answers we get for E will be multiples of 50. For example, if I go along this line, it's 0, 50, and we're only saying the Y values right now. 0, 50, 100, 150, 200, 250, 300. All of those are multiples of 50. Now that we hopefully understand the definition of partial variation, we can start to look at some of its characteristics. The first characteristic we'll look at is what does it look like when it's in a graph? What did the two graphs that we were working with have in common? Well, the first thing we can notice is that both graphs are a straight line. And they are straight lines because they both have rates of change that are constant. And here you can see the rates of change there, where in the first graph, for each change of 1 in the X value, the Y value changed by 2. And in the other one, each change of 1 in X, the Y value changed by 50. And so both graphs have straight lines. So all partial variation graphs will be straight lines because they have rates of change that are constant. The other thing we can notice is that the lines in both graphs go through the origin. The origin is the point 0, 0 on both graphs, and you can see it's circled there. Another characteristic of direct variation which we are going to focus on is how direct variation is reflected in tables of values. So what do these two tables of values have in common? And the answer to that question will reveal two important characteristics of direct variation. The first thing we can notice is that both tables of values have first differences that are constant. And so if we look here in the first table of values, you will see that the first differences are all going to be 2. Remember, the first differences is the difference between any two rows in the table of values. So the difference between 2 and 0, 2 minus 0, gives me 2. 4 minus 2 gives me 2. And you can see the first differences are constant all the way along the table of values. The second table of values also has constant first differences. In this case, they are all 50. So that's one very important characteristic of direct variation. Another one is that both tables of values have a row where X is equal to 0 and Y is equal to 0. And you can see them circled here. Now, this row doesn't have to be at the very beginning of the table of values. As long as this row exists anywhere in the table of values, and of course the first differences are constant in the table of values, that would mean that the table of values reflects a direct variation. I now want to turn your attention to a kind of problem that you will see in this unit and in the next. And that is a question where you need to determine the rate of change based on two quantities. Now, I want you to recall that another term we use for rate of change is the constant of variation. And so sometimes in the question you will see the words constant of variation, as you see here, where the question is the distance traveled by a bus varies directly with time. That means it's direct variation. The bus travels 240 kilometers in 3 hours. What is the constant of variation? So I'm going to show you two ways to solve this, and you can decide which you'd like to use. So first, I just want to point out that the equation for direct variation is y equals mx. Here we're being asked for a constant of variation, and instead of writing m, I can simply write k. Now if you left m, it's not a big deal at all. Now I need to think, which values of y equals kx do I know? Remember, y is the quantity for the dependent variable, and x is the quantity for the independent variable. Of 240 kilometers in 3 hours, which one is the dependent variable? Which one should be y? Well, the amount of kilometers travels depends on the amount of time. So y could be replaced with 240. And that means x could be replaced with 3 because x is the independent variable quantity and 3 is that quantity. So I could rewrite this equation as y equals k3, which we all know should be written as, 240 equals k3, which we all know should be written as 240 equals 3k. I can now use algebra to solve and find the value of k. And what would I have to do? I would divide both sides by 3. And when I divide both sides by 3, I would get 80 is equal to k. K, the constant of variation, is equal to 80 kilometers per hour. Now, what did I actually do here? In this case, what I did was I ended up dividing the y quantity, the dependent variable quantity, 240, by the x quantity, which was 3, and I got the answer. So you can see there's a bunch of extra steps here, when really all I needed to do was 240 divided by 3. So when you get these kinds of questions, a procedure you can follow would be to identify the dependent and independent variables by putting y and x over them. You could then write this formula, that the constant is equal to the quantity for the dependent variable divided by the quantity for the independent variable. In this case, it's 240 divided by 3, and therefore the constant of variation is 80 kilometers per hour. Let's try to summarize what we've learned thus far before moving on to some application questions. The first thing we've learned is the definition of direct variation. Direct variation is a relationship in which two quantities vary directly with each other. The dependent variable is a constant multiple of the independent variable, and it is also called a proportional relationship. As an equation, direct variation is in the form y equals mx, which can also be written as y equals kx, where k is a constant of variation, or another term that's used for k is constant of proportionality, but let's not stress out too much about that terminology. Next, we also learned that in a graph, the line representing a direct variation always goes through the origin, as you can see in the two graphs shown there. We also learned that in a table of values representing a direct variation, the first differences are constant, and if the table has a row with the value x equals 0, then y must equal 0 in the same row. And so if you look at the two tables of values there, it's not important if the zeros are at the very start of the table of values. As long as there is a row where it's 0, 0, and the first differences are constant, then you know for sure it's a direct variation. It's also possible to represent, however, direct variation with no 0, 0 in the table of values. What is important is that if there is a row with 0 for x, that the y value must also be 0. Lastly, we learned that with two quantities, one can determine the constant of variation with the expression k equals y over x, and we saw that just moments ago. The first question is this: which of the following situations describes a proportional relationship between two variables? Direct variation. Anthony earns $20 plus 50 cents for each bag of peanuts that he sells. Julie started with 100 candies and ate 4 per hour. Maria started reading a book and read 20 pages per hour. To rent a canoe, it costs $40 to reserve the canoe plus $15 per hour. Pause the video now and answer the question to the best of your ability. You should have got the answer. Maria started reading a book and read 20 pages per hour. This example with Marie is the only example where you would find the values 0, 0 for x and y. If Maria reads for 0 hours, she will have read 0 pages. If she read for 1, 20 pages, 2, 40, and you can see it's going to go up by 20 each time. So it starts at 0, 0 and goes up by 20 each time. All the 3 other examples, that is not true for. If we substitute 0 for the independent variable in all of them, you will find you do not get 0 for y. Therefore, they are not direct variation. The next question is, Donald earns $30 per hour. Which of the following equations represents the relationship between the hours he works and his earnings? E equals 20h, E equals 30h, H equals 30h, E equals negative 30h. Pause the video now and try to answer the question. The correct answer is E equals 30h, where E is his dependent variable. His earnings depends on the number of hours he works. 30 is your constant of variation, slope, or rate of change, and H is the number of hours he worked. The next question says, which of the table of values below reflects a proportional relationship, direct variation? There could be more than one correct answer. So look at the table of values, take a second, pause the video, and try to figure out the answer. You should get the answer that the second and the fourth tables of values are direct variation. If you look at them, you'll see they both have the row which has 0, 0, and they both have constant first differences. So in the one on the right hand side, the fourth one, you can see it's going down by 4 each time, and it has the row 0, 0. And for the second one, 0, 0, and it's going up by 4 each time. The first table of values is not direct variation because it does not have the row 0, 0. You can see when x equals 0, y equal to 3, therefore it cannot be direct variation. The third table of values cannot be direct variation because even though it has the row 0, 0, you can see the first differences are not constant. Here, but the difference between 0 and 6 is 6, but the difference between 6 and 9 is 3, 9 and 12 is 3. So 1 and 3 cannot be the correct answer. The next question, the graph shows the number of gallons of gas used for each mile traveled. What is the rate of change? Make sure to pay attention to the units. The possible answers are 20 gallons per mile, 0.05 miles per gallon, 0.05 gallons per mile, or 20 miles per gallon. Pause the video and choose your answer. The correct answer is 20 miles per gallon. And we can know that because if you look at the graph here, one gallon of gas was used for 20 miles that was traveled. So this means 20 miles per 1 gallon. Next question, Mr. Miller had no money, so he borrowed $5 a day from Mr. O'Connor. Which of the following is the equation that represents the relationship between days and Mr. Miller's net worth? The options are D equals 5n, n equals negative 5d, n equals 5d, n equals 10d. Pause the video and choose your answer. The correct answer is n equals negative 5d. N represents his net worth, and it's going to decrease by 5 each day that he borrows $5 from Mr. O'Connor. Last question. The total cost varies directly with the number of books bought. 5 books cost $35. What is the constant of variation? $7 per book, 20 cents per book, $6 per book, or 40 cents per book. Pause the video and choose your answer. The correct answer is $7 per book. And it's $7 per book because the dependent variable is the cost of $35, the independent variable is 5, and I divide the dependent variable 35 by the independent variable 5, and I get $7 per book. That's the end of this video. Hope it's helped you a lot. Good luck with your work.